Hello everybody, welcome to Hardware Horizon. In the last video, we talked about the basics of semiconductors. We also saw what are the different types of energy bands, charge carriers, and that in order to make semiconductors useful, we need to dope them with certain types of impurities. We saw that doping an intrinsic semiconductor with pentavalent atoms gives rise to N-type semiconductors, while doping them with trivalent atoms gives rise to p-type semiconductors. We ended that video with a brief mention of the p-n junction and how it forms the basis of all modern semiconductor devices. In today's video, let us pick up from there. So what exactly happens in a p-n junction? In order to understand that, let us consider a thin silicon wafer as shown. Now, if we dope the silicon wafer in such a way that half of it is p-type and the other half is n-type, something very interesting happens at the intersection. If you remember, and we have also discussed it in the last video, n-type semiconductors have electrons as the majority charge carriers. On the other hand, p-type semiconductors have holes as the majority charge carriers. These free electrons in the n region will have a natural tendency to move towards the holes in the p region. Why? Because electrons and holes can be thought of as opposite charges, and as you know, opposite charges attract. So to put it simply, the electrons from the n region will move across the junction, or if we are using more appropriate terms, will diffuse across the junction, reach the p side and recombine with the holes there. I hope you are with me until this point. Also, I think it is quite obvious that the electrons near the junction will find it way easier to do this whole journey as compared to the electrons that are further deep in the n region and away from the junction. So what exactly is happening is the free electrons in the n region, which are near the junction, will leave their atoms and move to the p side. Losing of electrons will generate some immobile, positively charged ions in the n region. This creates a region of positive charges near the junction in the n side. So what is happening in the p side? Well, it is a very similar concept. So the incoming electrons will recombine with the holes here. Gaining of electrons will generate some immobile, negatively charged ions in the p region. Similar to the n side, this creates a region of negative charges near the junction in the p side. Thus, at the p-n junction, a region is created that is reduced or depleted of any free charge carriers, and hence fittingly so, this region is called the depletion region. In reality, the depletion region is created in a very short period of time, and it is very thin as compared to the rest of the p and the n regions. Now, if you remember from your high school physics, when two opposite charges are brought closer enough, an electrostatic force acts between them. So in this case also, there will be an electrostatic force, a building potential because of the positive and the negative charges, and a resultant electric field starting from the positive charges and ending on the negative charges. So to do a quick recap, electrons from the n region will diffuse across the junction and recombine with the holes in the p region. This creates a region of positive charges in the n side and negative charges on the p side near the junction. The region thus created is called the depletion region, and it keeps getting wider and wider as more and more electrons diffuse from the n side to the p side. The widening of the depletion region keeps building up the potential in this region, and the electric field also keeps on increasing. This happens until the electric field becomes strong enough to oppose any more natural migration of the electrons from the n side to the p side. At this point, the junction is said to have reached equilibrium and the depletion region is complete. The built-in potential at which this happens is called the barrier potential, and it is around 0.6 to 0.7 volts for silicon. Now, if we want even more electrons to flow from the n side to the p side so that there is an electric current flowing through the p-n junction, we need to connect it to an external voltage with a potential that is equal and opposite to that of the barrier potential. This is called forward biasing of the p-n junction, and we will be discussing it in the next videos. Now, if you're still not clear with the entire concept, let us look at it from the perspective of energy diagrams. So before they are joined, the conduction and valence bands of the p side will be slightly higher than that of the n side. Even though they are at different levels, there's still an overlap between the conduction band of the p side and the n side. It is in this region of overlap that electrons can diffuse from the n to the p side. But while doing so, these electrons rapidly lose energy. So as soon as they reach the conduction band in the p side, they fall into the valence band and recombine with the holes there. This recombination leads to the creation of positively charged ions on the n side and negatively charged ions on the p side. And a depletion region is created whose built-in potential can be expressed as V naught equals to Vn minus Vp, where Vn represents the constant potential in the N side outside of the depletion region, and Vp represents the constant potential in the P side outside of the depletion region. Now we know that the product of the constant potential with the magnitude of charge per carrier gives its energy. Since electron has a negative charge, the product minus EVN represents a reduction in electron energies on the N side due to the formation of the depletion region. In contrast, the product EVP represents the increase in the electron energies on the P side. As during the formation of the depletion region, the energy levels on the N side keeps dropping down while that on the P side keeps going up. This is represented by a bend in the energy diagram. The slope of the bend keeps on increasing until there is no more overlapping of the conduction band of the N side and the P side. At this point, the junction is said to have reached an equilibrium and the depletion region is complete, and the electric field now exactly opposes the diffusion forces. Okay, so now that you have understood the p-n junction, you should know that these junctions form the basis of firstly diodes, which are one of the most widely used but also the most basic form of electronic devices. And I feel that the understanding of diodes is very important to understand more complex electronic devices. So we will be covering diodes in the next class. So in summary, in today's video, we saw what are p-n junctions and how they are formed, how the charge carriers moves during the formation of the p-n junctions. We also try to understand the concept better with the help of energy diagrams and gradually build up to understand why the p-n junctions are so important. As usual, you will find the notes and worksheets in the description box. If you have any questions, feel free to reach out to me or leave a comment in the comment section below. And if you like this video, don't forget to subscribe so we can continue on this journey. I will see you in the next video. Ta-da!